What if I told you that in 2017, something from another star system visited our solar system, and one of Harvard's top scientists believes it might have been sending us a message? Oumuamua, the first confirmed interstellar visitor, has sparked the most controversial debate in modern astronomy. When Joe Rogan sat down with physicist Avi Loeb, the conversation revealed shocking theories that challenge everything we thought we knew about our cosmic neighborhood. Today, we're diving deep into the mystery that has scientists questioning whether we've already encountered alien technology. The discovery that changed everything. October 19, 2017, marked a historic moment that most people completely missed. On that day, astronomers at the Pan-STARRS telescope in Hawaii detected something that shouldn't exist, an object moving through our solar system at impossible speeds, following a trajectory that proved it came from another star system. Named Oumuamua, meaning messenger from afar arriving first in Hawaiian, this mysterious visitor was unlike anything scientists had ever encountered. The object was traveling at 196,000 miles per hour, far too fast to be captured by our sun's gravity. Its hyperbolic trajectory confirmed what seemed impossible. We were witnessing humanity's first confirmed interstellar visitor. What made this discovery truly extraordinary wasn't just its origin but its timing. Astronomers estimate that interstellar objects like Oumuamua pass through our solar system about once per year, but they're typically too faint and fast to detect. Only recently had our telescopes become powerful enough to spot such visitors. The fact that we caught this one suggested either incredible luck or that these objects might be more common than previously thought. Within days of its discovery, Oumuamua would reveal characteristics that would divide the scientific community and spark debates that continue today. An object unlike anything we've seen. The more scientists studied Oumuamua, the stranger it became. This wasn't just another space rock. It was something that defied every category astronomers had for celestial objects. The object's shape was the first major anomaly. Based on how its brightness changed as it tumbled through space, scientists calculated that Oumuamua was extremely elongated, roughly 10 times longer than it was wide. To put this in perspective, imagine a cigar that's 1,300 feet long but only 130 feet wide. No asteroid or comet in our solar system has ever been observed with such an extreme aspect ratio. Even more puzzling was its behavior. As Oumuamua rotated every 7.3 hours, its brightness varied by a factor of 10, the most dramatic brightness variation ever recorded for a natural space object. This suggested either an incredibly unusual shape or surface properties unlike anything in our cosmic neighborhood. The object's reddish color, similar to objects in the outer solar system, indicated it had been wandering through interstellar space for hundreds of millions of years, its surface reddened by cosmic radiation. Yet despite this ancient journey, Oumuamua showed no signs of the dust or gas emissions typical of comets when they approach the sun. The acceleration mystery that baffled scientists. Just when astronomers thought they understood Oumuamua, the object delivered its most shocking surprise. It was accelerating away from the sun in a way that gravity alone couldn't explain. This non-gravitational acceleration was subtle but unmistakable. As Oumuamua sped away from our solar system, it was moving faster than it should have been based purely on gravitational calculations. For comets, this kind of acceleration is normal. Ice vaporizing from their surface creates a rocket-like effect. But Oumuamua showed absolutely no signs of cometary activity. The acceleration was consistent and measurable, ruling out random forces or measurement errors. Something was pushing Oumuamua, but what? Traditional explanations fell short. The object was too small for solar radiation pressure to account for the observed acceleration, and it lacked the outgassing that typically propels comets. This mysterious acceleration became the smoking gun that would fuel the most controversial theory in modern astronomy. If natural explanations couldn't account for Oumuamua's behavior, what could? The answer would come from an unexpected source, Harvard's Department of Astronomy, where one physicist was willing to consider possibilities that others dismissed as impossible. The stage was set for a scientific revolution that would challenge our understanding of our place in the universe. Avi Loeb's revolutionary theory shakes science. When Harvard physicist Avi Loeb appeared on Joe Rogan's podcast, he dropped a bombshell that sent shockwaves through the scientific community. Oumuamua might be artificial technology from an alien civilization. Loeb, former chair of Harvard's astronomy department, wasn't some fringe theorist. He was a respected scientist with hundreds of published papers, who had simply followed the evidence to its logical conclusion. Just like Sherlock Holmes, I follow the evidence, trying to find the solution. The physicist's theory centered on one key insight. Oumuamua's unusual properties perfectly matched what engineers would design for an interstellar light sail. Its extreme thinness would minimize damage from interstellar dust, while its flat geometry would maximize surface area for solar radiation pressure. Exactly what would propel a light sail through space? Loeb's calculations showed that solar radiation pressure could indeed account for Oumuamua's mysterious acceleration, but only if the object was incredibly thin, like a sheet of paper tumbling through space. This wasn't just speculation, it was based on rigorous physics and observations that other natural explanations couldn't adequately address. The scientific establishment's reaction was swift and harsh, but Loeb stood firm in his assessment.
The light sail theory that changes everything.
The concept that Oumuamua could be an alien light sail isn't science fiction, it's cutting-edge physics that we're already developing here on Earth. Light sails work on a simple principle. Photons from stars carry momentum that can push extremely thin reflective surfaces. Just as wind pushes a ship's sail, starlight can propel a spacecraft equipped with a large, lightweight sail. The technology is so promising that organizations like Breakthrough Starshot are developing light sail probes to reach nearby star systems. Oumuamua's behavior perfectly matched what scientists would expect from a light sail. Its acceleration was consistent with solar radiation pressure acting on a thin, flat object. The lack of outgassing made sense because artificial objects wouldn't contain volatile materials that vaporize near the sun. Even its tumbling motion resembled how a damaged or derelict light sail might behave after millions of years in space. Maybe it was just alien craft technology that unintentionally lost itself, like space junk. Loeb suggested, making the theory seem less threatening and more plausible.
The search for alien signals begins.
The possibility that Oumuamua might be artificial technology triggered the most intensive search for alien signals in modern history. Breakthrough. Listen, the world's most comprehensive SETI program immediately turned the massive Green Bank telescope toward Oumuamua. If the object was indeed artificial, it might be transmitting signals, either intentionally or as electromagnetic leakage from its systems. The search was unprecedented in its scope and sensitivity. Over multiple observation sessions, the telescope scanned billions of radio frequencies, recording a staggering 90 terabytes of data, enough to fill 23 high-end computers. The observations covered different phases of Oumuamua's rotation, ensuring that any potential signals from different parts of the object would be detected. The sensitivity was remarkable. At Oumuamua's distance, the telescope could have detected a signal as weak as a cell phone transmission. If alien technology was aboard this mysterious visitor, we would have heard it. The results were both disappointing and reassuring. No artificial signals were detected from Oumuamua. The object remained silent as it tumbled through space, offering no direct evidence of alien technology. However, the absence of signals didn't disprove the artificial hypothesis. A derelict piece of technology wouldn't necessarily be transmitting.
Why natural explanations fall short.
The scientific community's resistance to Loeb's alien hypothesis led to, well, increasingly creative attempts to explain Oumuamua through natural processes, but each explanation just seemed to create new problems. One theory suggested that Oumuamua was a hydrogen iceberg, basically a chunk of solid hydrogen that would sublimate near the sun, causing the observed acceleration. But, solid hydrogen couldn't actually survive the millions of years needed for interstellar travel, and the object didn't show any of the expected hydrogen emissions. Another proposal claimed Oumuamua was a fragment of a disrupted comet, but this idea couldn't account for its extreme elongation or the lack of any cometary activity. Some scientists even suggested it was a dust bunny, meaning a loosely bound collection of particles, but an object like that would have been torn apart by tidal forces during its close approach to the sun. The most recent theory proposed that Oumuamua was made of nitrogen ice, kind of like Pluto's surface. While this could maybe explain some of the observations, it would require the object to have originated from a Pluto-like world in another star system, which is, honestly, itself a pretty extraordinary claim. So, each natural explanation required increasingly exotic conditions or materials, leading some scientists to start questioning whether the artificial hypothesis might actually be the simpler explanation.
The implications of alien technology.
If Oumuamua truly represents alien technology, the implications for humanity are, honestly, staggering, and fundamentally change our understanding of our place in the universe. The object's properties suggest it wasn't sent to spy on Earth or, make contact. Its trajectory showed no signs of course corrections toward our planet, and it was already leaving the solar system when we discovered it. This supports Loeb's theory that we encountered cosmic debris, the equivalent of finding a piece of alien trash just floating through space. Strangely enough, this scenario might actually be more significant than active alien contact. It suggests that technological civilizations are common enough that their artifacts regularly drift through the galaxy. If Oumuamua is artificial, it implies that advanced civilizations have been building interstellar technology for, millions of years, leaving a trail of debris in their wake. The discovery would also validate humanity's own technological trajectory. We're developing light sail technology for interstellar exploration, which suggests that this approach represents a natural evolutionary step for spacefaring civilizations. Oumuamua might be showing us our own future, a time when human-built light sails will traverse the galaxy, potentially becoming mysterious visitors to other star systems.
The race against time and distance.
One of the most frustrating aspects of the Oumuamua mystery was just how quickly the opportunity to study it disappeared, highlighting the challenges of investigating interstellar visitors. By the time scientists realized Oumuamua's true significance, it was already racing away from the sun at, honestly, incredible speed. The object was moving so fast that no existing spacecraft could catch up to it for a closer look. Even our most powerful rockets would have taken decades to reach Oumuamua, and by then it would be way too far away to study effectively. This time, pressure forced astronomers to make critical observations with ground-based telescopes while the object was still detectable. Every day that passed meant Oumuamua was getting fainter and harder to observe. The window for detailed study lasted only a few months before the object became too distant for meaningful analysis. The experience taught scientists some valuable lessons about preparing for future interstellar visitors. New detection systems are being developed to spot such objects earlier, giving researchers more time to study them. Space agencies are also considering rapid response missions that could be launched quickly to intercept future visitors before they escape our solar system.
What Oumuamua means for the future.
Oumuamua's brief visit has, without a doubt, fundamentally changed how we think about interstellar space and our search for extraterrestrial intelligence, regardless of whether it was natural or artificial. The object proved that interstellar visitors are detectable with current technology, opening a whole new field of astronomy. Scientists now know what to look for and have developed protocols for studying future visitors more effectively. The recent discovery of additional interstellar objects, including Comet 2I Borisov and the newly detected 3I Atlas, shows that Oumuamua wasn't a unique event. If Oumuamua was indeed artificial, it suggests that the galaxy might be filled with technological artifacts from ancient civilizations. This archaeology of the galaxy approach to SETI represents a new way of searching for evidence of alien intelligence, not through radio signals, but through physical artifacts drifting through space. The controversy surrounding Oumuamua has also highlighted the importance of keeping an open mind in science. Loeb's willingness to consider unconventional explanations, despite professional criticism, really demonstrates the value of following evidence wherever it leads. As we continue to develop our own interstellar technology, Oumuamua serves as a reminder that we might not be alone in this cosmic endeavor. From its mysterious acceleration to its impossible shape, Oumuamua challenged everything we thought we knew about our cosmic neighborhood. Whether it was a natural phenomenon or humanity's first encounter with alien technology, this interstellar visitor opened our eyes to possibilities we never imagined. As Joe Rogan and Avi Loeb showed us, sometimes the most extraordinary explanations deserve serious consideration. The truth about Oumuamua may remain a mystery, but its impact on science and our understanding of the universe will last forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic mysteries. A cosmic alignment so perfect it defies chance, or a deliberate arrival we were never meant to see. On September 12, 2025, astronomers witnessed the impossible. Two colossal objects arriving from opposite ends of the universe set to rendezvous in our solar system during a total observation blackout. The official story is twin comets, but the evidence points to something far stranger. Let's explore this together. The Swan's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge, this was a spectacle. News ignited across astronomy networks, and just 2 days later an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. A name makes it real but can also deepen the mystery. By September 13th, the International Astronomical Union's Minor Planet Center made it official, designating the object C/2025 R2 or SWAN in honor of the instrument that found it. Within a single weekend, the global astronomy community, from professionals using the Hubble Space Telescope to amateurs in their backyards, was completely fixated on this celestial titan. They traded images and brightness measurements across hemispheres, trying to make sense of its unprecedented behavior. Most comets discovered in the modern era are faint smudges requiring powerful telescopes, but SWAN was a spectacle for anyone who knew where to look. Its magnificent tail sliced through the constellation Virgo at a blistering pace of 20 arcseconds per minute, growing brighter with each passing day as it raced toward the sun. The conversation quickly shifted from simple observation to intense speculation, with astronomers like Dr. Robert Warwick, the discoverer of Oumuamua, noting the statistical improbability of such a bright object appearing with so little warning. The amateur community, often the first to notice unusual behavior, was already debating what could possibly power a tail this long and this bright. It was simply too big, too vivid, and too fast to be ignored. The cosmic coincidence. Some things are so unlikely they stop looking like a coincidence. C/2025. R2. SWAN is not the only strange visitor this October. Days before, another object, 3I/Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. SWAN's path traces back from Aquarius while Atlas entered from the direction of Sagittarius. Yet both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 AU. For SWAN, it's just 3 days later, around October 20th, at a much closer 1.0 AU. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with SWAN's path tilted more than 60 degrees and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in spacetime that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So what happens when an object refuses to follow the laws of physics as we know them? 3I/Atlas first caught astronomers' attention by breaking all the rules. Early spectrographs from the Atacama Large Millimeter Array reported something that really set off alarms: a body dominated by nickel with virtually no iron, a ratio that's just unheard of in natural celestial objects. This, honestly, contradicts everything we know about comets and asteroids, which almost always contain iron-nickel blends, similar to chondritic meteorites. The claim was so radical that some labs immediately called for data re-verification. The mystery only deepened when its coma was found to be pumping out carbon dioxide, detected at a strong 4.3 micron spectral line, at rates 5 times higher than water. But what really couldn't be explained was its motion. Observers noted 3 distinct non-gravitational accelerations, each providing a delta V of several meters per second. These weren't the gentle pushes from solar heating, they were sharp, sudden bursts, almost as if the object had fired a thruster. The only other object that showed similar acceleration was Oumuamua, but as Harvard astronomer Avi Loeb pointed out, the pulses from Atlas seemed far more controlled and powerful. Swan, the fortress. If Atlas is a nimble drone, then Swan is a battleship. The scale of C/2025 R2 is, honestly, hard to comprehend, but it's the data that paints a radical picture. One that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. Swan's core has an albedo or reflectivity far higher than a typical dark comet nucleus, matching the signature of polished metal. Some analysts even argue it fits a nickel-cobalt blend, an alloy used for its immense strength. Then came reports of a silvery halo around the nucleus, an anomaly some interpret as a plasma envelope or an electromagnetic shield. This is where it earned the nickname, the Fortress. Unlike Atlas, Swan appears steady and invulnerable, refusing to fragment as it nears the sun. Even its tail shows evidence of micro-thrusts, tiny rhythmic pulses at a consistent frequency that defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and on a deliberate, powered course. It isn't just passing through, it's arriving. Mission theories. Coincidence or a coordinated mission? When a long-period object on a 22,554-year cycle and a hyperbolic interstellar object arrive together, the odds of chance really plummet. This has fueled a wave of mission theories. The first, and most routine, is a scheduled refueling run, with the sun acting as a cosmic pit stop for 2 engineered probes. A second, less peaceful theory suggests an intervention or a confrontation, especially given the incredible power levels required for their observed accelerations. A third theory, championed by thinkers like Dr. Avi Loeb, proposes an audit chain. Oumuamua, or 1I/2017 U1, was the first scout, followed by 2I/Borisov, and now Atlas and Swan represent escalating responses to Earth's century of radio transmissions. Each new arrival would be a more complex probe sent to check in. In every scenario, the sun isn't just a backdrop, it's the rendezvous point, the power source, and the beacon. The idea of using a star for a gravitational assist or energy top-up is standard practice for our own probes, like the Parker Solar Probe, making this theory, honestly, chillingly plausible. Ancient connections. An orbit of 22,554 years is, well, a link to a different chapter of human history. The last time Swan would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. This is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a pretty controversial theory that its pillars are actually an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. Mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If Swan is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just as things get interesting, the lights go out. From October 8th to 18th, both Swan and Atlas will pass through solar conjunction, meaning the sun's glare makes them impossible to observe for optical telescopes on Earth. This affects every major observatory, from the Very Large Telescope in Chile to the Keck Observatory in Hawaii, as the objects will be within a solar elongation angle of fewer than 5 degrees. This is a normal astronomical occurrence, but honestly the timing is incredibly convenient. Rumors are circulating of internal memos from agencies like US Space Command and the European Space Agency, directing teams to suspend high-resolution imaging. Proposals for alternative observation methods have allegedly been denied and raw data requests delayed. A handful of telescope allocation reviewers speaking off the record have described explicit orders to avoid public statements. The result is a forced silence at the exact moment when the two most anomalous visitors in modern history make their closest approach, leaving a frustrating and highly suspicious gap in the data. Underground resistance. When the official channels go dark, the people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums. Keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's honestly a powerful narrative of decentralized science, a global network ensuring no data disappears. When Swan and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy, because, wow, the numbers are staggering. The biggest red flag for both objects is the power source required to explain their behavior. If the observed accelerations of Atlas are indeed powered by thrusters, the energy output would need to be on the order of 10 gigawatts. That's the equivalent output of 10 large nuclear power plants like the Palo Verde generating station. But Swan makes that number look insignificant. Based on its size, brightness, and the micro-thrusts detected in its tail, the most extreme estimates place its power output at a mind-boggling 10,000 gigawatts, or 10 terawatts. That is more raw power than the entire energy grid of planet Earth combined. From a physics perspective, as noted by futurists like Dr. Michio Kaku, such energy control would place its creators firmly on the Kardashev scale as a Type 1 or even Type 2 civilization. These figures push the conversation beyond academic debate and into a realm that, honestly, forces us to question everything we thought we knew about our place in the universe. The facts are as clear as they are unnerving. Two anomalous objects, defying all statistical odds, have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official, top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech. Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work, and what secrets they're hiding in their depths.
The mysterious central storm discovery.
Buried beneath Jupiter's great red spot lies something that has left planetary scientists, honestly, speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. the discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined.
The beginning of the mission.
August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral, aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant.
Jupiter is the world of chaos.
Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere.
Io, the volcanic moon.
Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided honestly just unprecedented views of Io's volcanic activity, revealing eruptions that really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close.
Research on Jupiter's magnetic field.
Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerny from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions.
Juno mission peaks under Jupiter's surface.
Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away.
Jupiter's formation and composition.
Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior, where extreme pressure and temperature create conditions unlike anywhere else in the solar system.
Jupiter as Earth's protector.
Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life.
The Great Red Spot Mystery.
The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere.
Jupiter's deep atmospheric layers.
Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration.
Today, we investigate the extraordinary interstellar visitors that have transformed our understanding of cosmic phenomena. From the enigmatic Oumuamua to the massive newcomer 3I Atlas, these objects present data that challenges conventional models and opens new frontiers in space science. Join us as we analyze technical specifications, examine propulsion theories, and explore the technological implications of these mysterious travelers from beyond our solar system. Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS telescope array in Hawaii detected an unprecedented object exhibiting characteristics unlike any previously catalogued celestial body. Oumuamua, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, displayed non-gravitational acceleration patterns inconsistent with standard orbital mechanics. Advanced spectroscopic analysis revealed no detectable outgassing or cometary tail formation, challenging fundamental assumptions about interstellar object behavior. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that this visitor might represent an artificial light sail utilizing solar radiation pressure for propulsion. Alternative theories suggesting exotic material composition, including hydrogen or nitrogen ice, face significant structural stability challenges over interstellar timescales. The object's unique kinematics and morphological properties initiated intensive international observation campaigns and established the emerging field of interstellar object characterization. Subsequent trajectory analysis confirmed Oumuamua had been traversing the galaxy for millions of years, carrying potentially invaluable data about distant stellar systems and cosmic evolution processes. UFO-UAP encounters and theories. Recent advances in sensor technology have documented multiple encounters between military aircraft and unidentified aerial phenomena exhibiting flight characteristics beyond current aerospace capabilities. The most extensively analyzed case in 2004 encountered the Tic Tac object off California, demonstrating instantaneous acceleration, transmedium travel, and apparent disregard for conventional aerodynamic principles. Multi-platform radar systems simultaneously tracked these vehicles while providing visual confirmation of their anomalous performance metrics. Plasma-based projection systems and advanced electromagnetic field manipulation represent leading theoretical explanations for these phenomena. Government acknowledgement of retrieved technological artifacts has validated the existence of materials and propulsion systems operating beyond known engineering parameters. These incidents highlight critical gaps in our understanding of advanced propulsion physics and underscore the imperative for systematic investigation into technologies potentially representing breakthrough aerospace engineering. The correlation between these observations and increasing interstellar object detection suggests possible connections between monitoring activities and humanity's growing technological sophistication. Bob Lazar analysis. Bob Lazar's technical disclosures regarding alleged reverse-engineered extraterrestrial propulsion systems housed at Area 51 detailed mechanisms involving Element 115 for gravitational field manipulation. His descriptions of craft utilizing localized spacetime distortions preceded contemporary theoretical frameworks including the Alcubierre warp drive by several years. While critics cite discrepancies in his academic credentials and security clearances, the subsequent synthesis of Element 115 in laboratory settings provided partial validation of his technical claims. Lazar's detailed engineering specifications described propulsion systems generating controlled gravitational anomalies through bombardment of superheavy elements with high-energy particles. Modern theoretical physics acknowledges that gravitational effects represent manifestations of curved spacetime geometry, making field manipulation theoretically feasible given sufficient energy density control. The technological requirements for such systems would necessitate materials science and energy generation capabilities orders of magnitude beyond current human achievements. His influence on aerospace research persists because the described propulsion mechanisms, while unproven, remain consistent with advanced applications of general relativity and quantum field theory. Light sail hypothesis. Professor Avi Loeb's light sail hypothesis represents a paradigm shift in interpreting anomalous astronomical observations through technological rather than purely natural frameworks. Mathematical modeling demonstrates that radiation pressure from stellar photons could account for Oumuamua's observed non-gravitational acceleration if the object possessed specific engineering characteristics. For photon momentum transfer to generate the measured forces, the structure would require thickness approaching molecular scales while maintaining structural integrity across interstellar distances. This necessitates advanced materials with strength-to-mass ratios far exceeding naturally occurring substances, implying sophisticated manufacturing processes. Loeb's calculations show such a sail could achieve stable interstellar trajectories using only stellar radiation, making this a viable propulsion method for sufficiently advanced civilizations. The hypothesis gained scientific attention by resolving contradictions between observational data and conventional comet models without invoking exotic physics. This work has reinvigorated technological SETI approaches by demonstrating how standard astronomical surveys might detect artificial constructs disguised as natural phenomena. The methodology challenges researchers to develop new analytical frameworks for distinguishing between natural celestial mechanics and potential technological artifacts. 3I Atlas, the new discovery. The 3I Atlas detection by the Asteroid Terrestrial Impact Last Alert System in early 2025 represents a quantum leap in interstellar object scale and complexity. Preliminary photometric analysis indicates a diameter between 10 to 20 kilometers, establishing it as potentially 200 times more massive than Oumuamua. Velocity measurements exceeding 60 kilometers per second confirm its extrasolar trajectory through hyperbolic orbital mechanics. Advanced spectroscopic data from the James Webb Space Telescope reveals surface compositions suggesting metallic construction with anomalous thermal emission patterns inconsistent with natural asteroidal or cometary materials. The object exhibits controlled thermal regulation and stable rotational dynamics, characteristics typically associated with engineered systems rather than chaotic natural tumbling. Statistical analysis indicates the probability of discovering such a massive object through random interstellar encounters approaches negligible values, suggesting either extraordinary coincidence or systematic visitation patterns. Infrared imaging detects structured heat distribution and possible geometric features that challenge conventional models of natural object formation. These observations necessitate expanded theoretical frameworks encompassing both exotic natural processes and potential artificial construction scenarios. Atlas Telescope System. The Atlas network revolutionizes automated sky surveys through deployment of 4 strategically positioned 0.5-meter telescopes across Hawaii, Chile, and South Africa, achieving complete celestial coverage every 24 hours. Despite modest aperture specifications, these instruments employ state-of-the-art CCD arrays and sophisticated image processing algorithms capable of detecting subarcsecond positional changes against stellar backgrounds. Real-time data processing utilizes machine learning protocols trained on millions of astronomical images to identify anomalous motion signatures indicative of fast-moving objects. The University of Hawaii manages this network with NASA funding, establishing new paradigms for distributed observation systems. Atlas technology demonstrated exceptional capability in early detection of 3I Atlas, providing crucial lead time for coordinated international observation campaigns before the object's closest approach. Automated detection algorithms process terabytes of nightly data, flagging suspicious objects within hours of observation for immediate follow-up by major observatories worldwide. This high-cadence survey methodology has transformed asteroid detection from periodic manual searches to continuous automated monitoring, dramatically increasing discovery rates of rare cosmic phenomena and potentially hazardous objects. Scientific theories and debates. The astrophysical community remains divided over 3I Atlas classification, with competing hypotheses attempting to reconcile observational anomalies with established physics. The hydrogen iceberg model proposes exotic solid-state hydrogen formation in deep interstellar space, though structural mechanics calculations indicate rapid sublimation rates incompatible with observed stability. Nitrogen fragment theory suggests compositions analogous to Pluto's surface materials, potentially explaining thermal signatures without conventional outgassing patterns. Dr. Alan Fitzsimmons advocates natural origin interpretations while emphasizing the critical need for comprehensive spectroscopic datasets before considering exotic explanations. Fundamental inconsistencies persist between measured acceleration vectors and detectable volatile emission rates, challenging basic cometary physics models. Statistical mechanics analysis reveals discovery probabilities for objects of this scale through random encounters effectively approach zero, forcing reconsideration of either size distribution models or visitation patterns. Advanced computer simulations struggle to reproduce observed characteristics using purely natural formation processes, suggesting either unknown physics or engineered construction. Future detection technology. The Vera C. Rubin Observatory in Chile represents next-generation astronomical detection capabilities, featuring an unprecedented 8.4-meter primary mirror integrated with a 3.2 gigapixel wide-field digital camera system. The Legacy Survey of Space and Time protocol systematically images the southern celestial hemisphere every few nights across a decade-long mission timeline. Advanced machine learning algorithms process massive data streams in real time, enabling identification of transient events, near-Earth asteroids, and faint interstellar visitors within hours of observation. Rubin's enhanced photometric sensitivity extends detection thresholds to previously inaccessible magnitude ranges, promising discovery rates of dozens of new interstellar objects annually rather than current rates of one every few years. Automated processing pipelines utilize neural networks trained on millions of astronomical images to distinguish genuine cosmic phenomena from instrumental artifacts and atmospheric interference. This technological revolution enables detection of interstellar visitors during approach phases months or years before closest approach, providing unprecedented preparation time for detailed observation campaigns. Theoretical implications. 3I Atlas detection catalyzes profound theoretical implications across astrophysics, astrobiology, and SETI research paradigms. Statistical analysis suggests these discoveries may indicate a broader population of interstellar travelers, potentially including artificial constructs deployed by advanced civilizations. Galactic archaeology models now incorporate possibilities of technological artifacts traversing between stellar systems, fundamentally altering understanding of interstellar material exchange mechanisms. The concept of automated probe networks gains credibility when considering the efficiency advantages of robotic exploration versus biological travel across cosmic distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, systematically monitoring emerging technological species while maintaining operational security. The temporal correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about directed observation versus random encounters. These paradigms suggest humanity may be embedded within a complex, interconnected cosmic ecosystem where intelligence actively monitors and potentially influences emerging civilizations through strategic deployment of monitoring technologies. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's inaugural attempt at planned rendezvous with interstellar visitors, utilizing advanced trajectory prediction algorithms and rapid deployment capabilities. International coordination protocols integrate ground-based observatories with space-based assets, creating real-time global response networks optimized for comprehensive data collection during rare encounter opportunities. NASA's proposed rapid response spacecraft concepts could achieve launch readiness within months of detection, employing ion propulsion and gravitational assist maneuvers to intercept objects before solar system egress. Project Lyra, designed for Oumuamua pursuit, demonstrates technical feasibility of interstellar chase missions using current propulsion technology and precise orbital mechanics calculations. Advanced sample return architectures would enable direct laboratory analysis of interstellar materials, potentially revealing formation conditions in alien stellar environments or evidence of artificial construction techniques. Future missions deploy sophisticated analytical instruments including mass spectrometers, neutron activation systems, and high-resolution imaging arrays capable of determining composition, internal structure, and manufacturing signatures with unprecedented precision. These endeavors position humanity for transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about cosmic intelligence. The technical analysis of interstellar visitors like 3I Atlas continues pushing the boundaries of aerospace engineering and astrophysics. As detection capabilities advance and propulsion technologies evolve, we approach revolutionary discoveries about advanced materials, exotic physics, and potential cosmic intelligence. Whether these objects represent breakthrough technologies or exotic natural phenomena, they're already transforming our approach to interstellar exploration. Stay connected with Stellar Tech as we decode the engineering marvels hidden in cosmic mysteries and explore humanity's technological future among the stars.